So, welcome. Okay, yeah, right. This is the way. This is the Monday morning. Yeah. Okay. Anyway, this is week number 8, I believe. Hard to believe that it's already week number 8. Today we're going to do more primary decompositions. So we went through it, but did a bunch of it last time. I'm going to just remind you of a couple things, and then we're going to do 2 examples today. The first one is going to be monomial ideals and simplicial complexes. That'll probably take a good chunk of the first hour. And then the 3 problems that I have here. So I don't know if I just asked Lynn to put that up online. So if you're not here at the moment, I might have to email it to you at the break if she doesn't get a chance to do that. And so monomial ideals and simplicial complexes. And then the other example we're going to do, which both of these turn out to be really important in the general case somehow. And the other one is going to be 0-dimensional ideals. I mean, that seems just so boring in some ways, right? 0-dimensional, that's just a bunch of points. How can we do it? But it turns out that once we have these things, more of this one is going to be used in the general case, but we will actually use some of this as well. But this thing here will give us the technique for doing them in general. In general meaning in the case that we've been considering so far, polynomial rings over a field. On the other hand, it does generalize a bit more than that, but we'll consider this. Okay, so now let's just recall from last time. So I'm not going to recall what a prime ideal is, primary ideal. Now I'm assuming that you really know those things. However, we have that I is equal to Q1 intersect Q2 ... say QR is a primary decomposition of PD, so a irredundant primary decomposition if well, that intersection holds, but each QI is P sub I primary. Remember what that means? That means that, well, it has to be primary and its radical is Pi, which is a nice prime. 2, it's irredundant. So P1 up to PR are pairwise distinct. If you remember, if we had 2 different primary ideals with the same one, you intersected, it is also primary. So we can just combine the ones together. And 3, it's irredundant, meaning that I is not equal to the intersection of Q sub i's for I not equal to J for each J. Okay, so if I pick one of these out and I intersect the rest of them, it's not I. If it were, we'd just get rid of that term. Okay, so this is a primary decomposition. And our goal is to essentially compute those things and understand it a bit better. But first, before doing that, there are a few things. So what is unique about this? Okay. If I had us each go away and compute a primary decomposition for a specific ideal, and we got different ones, which we would possibly, what would be the same about each one? Okay. What is unique about ? That doesn't make a whole lot of sense. What is unique about this primary decomposition? In other words, what can we say? So if you recall also, recall from last time, that if I take Q is a primary ideal, Q colon F we could do it with just a single f or with f infinity. Let's do f infinity just because it's easier to write down and remember. This was either equal to the whole ring R or the or Q. Okay. And what were the cases? So when was this for which f is this equal to R? It's actually for any f in the prime P, right? So because some power of it will be in Q, and then consequently that's going to be it. And this is if f is not in P, then in fact, since it was primary, we would get just Q on its own. There would be no possibility of change. Okay, so this is pretty good. So there's a few more definitions we need about this this set of things. So two more definitions. And we're not going to quite prove, this would be more of a, in a class on commutative algebra, but in fact, you have enough of the things you could prove these at the moment. So the first one is, so define a minimal prime. So this is given an ideal I contained in R, and it's not the whole ideal because we're not doing anything with those things. This is ideal had to be, all the Q's are proper, so there's no way that this could ever be equal to the ring anyway. So define a minimal P, a minimal prime P of I as follows, to be an ideal, to be a prime ideal, well, P, such that I is contained in P, okay, but nothing else is between it. But if I is contained in P is contained in P prime, P prime is contained in P, and this is not equal, and P prime is prime, that doesn't happen. So I should maybe say this. I'll just say it's contained in there. That implies that P prime equals P. So those are the minimal primes covering containing P. Okay, so e.g., if I take I is equal to x times y squared, that's equal to x intersect y squared, and the ideal x and the ideal y are both minimal primes. By the way, unfortunately, I do not have these notes nicely written down in the Jupyter notebook that I still plan on making one out of. Well, this stuff is still in, but the stuff later on will not be. Okay, so that's a minimal prime of I. There's always a finite number of them. And the second thing is P, and how do I want to say this? An associated prime ideal of I is a prime ideal P such that P is equal to I colon F for some F. Okay. Now it's kind of interesting here. This is a prime ideal. So many ideals of the form, if I take I and I just start constructing I colon F's, I will oftentimes not get prime ideals. But sometimes I will get prime ideals. And anytime I do, I call that an associated prime. We could actually also say that this is equivalent, since R is Noetherian, and I'm not going to prove this, to that that I colon F radical is prime. Okay, when I say that, I mean that P is equal to this. So P is either equal to I colon F, or you could say it's the radical of such a thing. I'm not saying that very well, but if I look over all ideals of this form, I get what are the associated primes. And if I look over all ideals of this form and take the ones that are prime, I also get the set of associated primes. Okay. And we usually, I should have said that MIN of I will equal the set of minimal primes. And ASS of I is equal to the set of associated primes. You can tell how much of a mathematician you are if you don't laugh at that. But anyway, this is the standard notation for it. Okay. So these are two definitions of minimal primes and associated primes. Notice that they don't depend on a primary decomposition at all. This is just determined as the smallest ideals containing that are prime. And these are all containing it as well, but there might be more in this set. So let's do an example. How about I is equal to x squared comma xy? That's one of our sort of favorite kind of examples, because it sort of has a lot of behavior. What are the minimal primes of this? And what are the associated primes? So we need things that of the form, well, we want smallest ideals that are contained inside of this. That this is contained inside of. If it's a prime ideal, it's going to have to, if it contains x squared, it's a prime ideal, it has to contain x. So in fact, one of the primes is the ideal generated by x. Okay. Any others? Well, actually, no. Not for minimal, because since x squared is in there and we have that ideal here, any other prime that contains it will have to contain this thing. So that's really the only one. Okay. What about associated primes? If I start taking colon of this with things, I can only think of two things that I could take colons with, x and y. But that's because of the monomial ideal. In general, you don't have that kind of luxury. It's actually kind of a complicated mess. But if you take colon x, what do you get? Yeah, I get xy. And if I take colon y, just x. And actually, it turns out that's it. Okay. Although it's not completely clear how to prove that at the moment. Okay. So anyway, these are things. Note here in this example that every minimal element in here is contained in is an associated prime, but it's not equal in this example. Okay. And now I'm just going to state the theorems which you actually can prove using this kind of thing with the fact that we have a primary decomposition. In fact, it's a good exercise. So facts / exercise. 1. Okay, so we're given I is equal to Q1 intersect QR. QI is P primary. QI is PI primary. And this is an irredundant primary decomposition. Okay. The associated primes of I is actually equal to the set of the P's that occur. In other words, that piece of information of which primes actually occur, if I do one and you do one, we're gonna get exactly the same set with 97% probability, because the other 3% of the time I would have screwed up. Okay, so any rate, so we have this kind of thing. So that means all of these are prime, and then but there might be containment of these. Like here, the xy is contained inside of x. So if I look at if I take then the min of I, this is equal to the set of minimal elements under inclusion of the associated primes. Okay. It's actually an interesting problem to make sure that you can get these as I colon Fs. Okay. It's a little easier to get them as I colon F radicals of I colon Fs, but the reason, the way you can sort of see how you might do it is you take an element in the intersection of all the primes except for one. Now you need a little bit of commutative algebra to make sure that that's not in the other prime, but that's a thing called so hint. If you don't know it, look up, but use prime avoidance, which is a kind of nice set of little results that basically say that one prime can't be, if it's contained in the intersection of a bunch of other ones, it has to be contained in one of them. Okay. And also in terms of a union, there's a couple different things that go under this name. Or for me, they go under this name, probably not everyone. But at any rate, this is that's that. Okay, so that will give you, if you do it right, that'll give you that all of these will be associated primes, and then you can. That doesn't necessarily prove that this is there. So it needs a little bit more to prove it. But I think you can still do it with all of these things. So anyway, this is the fact. Now, so here's some sort of terminology. Minimal primes are also called isolated primes. That's one thing. And associated primes that are not minimal are called embedded primes. So the isolated minimal are synonymous, and embedded are all the other ones. So we have four notions: associated prime, minimal prime, isolated prime, embedded, but there's only three notions. Okay, and so for instance, in this example, what do we have? XY is an embedded prime. Okay, now I think we need to move the camera. Okay, so anyway, there's a lot. Let's see, what else do I want to say about this? Here's a little remark. If I is equal to Q1 intersect ... intersect QR is a primary decomposition, and let's say QI is PI primary, then what is the radical of I equal to? Well, if you think about it, it's the intersection of all these primes. But since I intersect X and I intersect with XY, I get X again. I don't need all of those things. So this is actually equal to the intersection of all P sub I, where PI is isolated or is minimal. Or maybe I should say is in min of I. Okay. So this is a general fact that we will oftentimes, in order to compute this, we will compute radical of I first, or compute these guys, the minimal primes, and then we'll go back and try to get the rest of the stuff. Let's do a very simple example first. So let's say R is equal to K of X. Okay. This you might think is funny, and actually it is kind of. So R is a UFD and a principal ideal domain. It's got everything nice going for it. Okay. It's in fact it's so nice that it's kind of boring. Okay, so but anyway, so if F, so everything in here is so if F is in R, so I is equal to F then, right? That's the only every ideal is of this form. Since it's a UFD, we can factor this uniquely. So we can factor F, and how do I do it uniquely? It would be a constant C times some, do I want to use F1? I guess it doesn't matter what I use. Let's use, I don't know why P is supposed to stand for irreducible polynomial. I think it's supposed to be prime polynomial, but at any rate, it's just to match it for over the integers. But so we'll do P1 of X to the M1 dot 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 PR of X to the MR. So where C is some field element, and P1 up to PR are irreducible polynomials. And the M's are greater than or equal to 1. In other words, so this is unique up to order. And I've already forgot one thing though. These are irreducible polynomials, pairwise distinct. Irreducible monic polynomials, pairwise distinct. I have lots of ways I can say this, but this is one of them. Okay, I have to do something to make this unique. If I factor out so they're all monic, then in fact I get something like this. Okay, we will assume that we're working over that computationally we can do this. Okay, for whatever field we want. That's not a foregone conclusion, and in fact, it turns out that one good way of doing this for more complicated fields K than just the rationals or Z mod P or something like that is to do a primary decomposition kind of thing and then use that. So we will see how that relates. Maybe, but not today. Okay, so any case, so what are the so actually what is the whole point wasn't the factorization, it's what's the primary decomposition here. So so then a PD of I, which is F, is the ideal generated by P1 to the M1 intersected dot 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 intersected with PR to the MR. Okay, which of these are isolated primes and which are embedded primes? Pairwise distinct actually even means more in this case, by the way. Even have PI plus PJ is the actual unit ideal, it's the R itself. Okay. So in fact, these are all so the minimal primes of I is the associated primes of I, and it is just the set of all these P1 to PR. So, so this is a pretty straightforward case. These are all primary ideals then, and in fact, this is completely unique. There is no other ideal that you could put here that would give you a primary decomposition. In fact, actually, I'm not going to say that right at the moment, but if I have a minimal prime here, then I have its associated primary ideal. Using ideal quotients, you can prove that that primary ideal Q corresponding to it is unique as well. So it's only the embedded primes that have this non-uniqueness associated with it. And there's even more you could really say about uniqueness of it, but it's not really relevant for what we're doing. So we're going to leave it out. Any questions about this stuff so far? So today we're doing so-called, quote, trivial cases. Trivial case number one is this thing. Trivial case, quote, number two is monomial ideals, which is anything but trivial. Let's see, is there something else I wanted to say that I'm forgetting about? No, I think that this is a good place. So now we're going to do sort of, yeah, I think we're going to do now simplicial complexes. And Stanley-Reisner ideal. So everyone lately has been calling it Stanley-Reisner ideal rather than Reisner because it looks like it should be a Reisner, you know, some nice German name. But then everyone's been calling it from that. Mel Hoxter said actually he's from the Bronx, like it's like Jerry Reisner, and so everyone started calling it Stanley-Reisner ideal. But then it turns out that someone actually saw him and said, no, he pronounces his name Reisner. So I have no idea which is correct. I didn't ask him personally, so I don't know if that's true. But in any case, I'm not, you know, whatever. Okay, so it's Stanley-Reisner or Stanley-Reisner. I learned Reisner originally, so that's sort of what I tend to use. Okay. And so what we're going to do now is just talk about this. So we're going to talk about, so I'm going to define a simplicial complex. The basic idea is really straightforward. In topology, you have a surface. And a surface can be a very complicated object geometrically. But if I sort of put triangles on it and approximate it in some sort of piecewise linear manner by a whole bunch of triangles, I can really figure out what's really going on. It changes topology into a combinatorial subject, and it's just a really awesome idea. And so, and that's all done through, well, the first case that one does is simplicial complexes. Then there are cellular complexes, but they have their own problems with them. So this is a nice one to start with. Okay, so definition. An abstract. So you oftentimes in topology, a simplex will be you map a simplex, which is just a triangle or a tetrahedron or something, into your space in some nice way. But we ignore that. We just are going to look at the abstract set. An abstract simplicial complex. Delta. And actually, we typically, once we define it, we never really use the word abstract anymore. Okay, on a vertex set, V, which often for us is going to be either 1 to n, 0 to n minus 1, or maybe a bunch of variables in a ring or something like that. So, but at any rate, it's just a vertex set V, such that, let's see, is a set of subsets of V itself, such that two things hold. Ooh, actually, I don't like the first one anymore. I really don't like the first one. The typical thing is you might say, the set I is contained in delta, but that's not really that for every I. So that for every vertex in V is in the simplicial complex. We don't necessarily, I don't see why we want that. So I don't know why I wrote that down. So such that, and then so the only condition is that if sigma and tau, if sigma is in delta, remember that makes it a subset of V itself, and tau is a subset of sigma, then in fact tau is also in. Okay, that's the only condition. You might be interested. I mean, if a vertex is not in there, you could sort of ignore it. But really, I think we want to make sure to compare different ones. You want to allow the possibility that it's on a different set of a smaller set of variables. Okay, so each sigma in delta is called a face of delta. And then there's a whole lot of other little notions. So a non-face of sigma is a subset of V such that sigma is not in V in delta. Okay, so this face, non-face is just all the rest of the things. There's also going to be co-face and things like this, so which we'll talk about later. But before doing that, let's do an example. I'm going to choose, finally, color. I'm going to choose, I don't know if the color will help, but at any rate, so here are going to be, V is going to equal 4 vertices, say 1, 2, 3, 4. And these are going to be them. And the first, I'm going to put this guy here is a triangle, and that's going to be in my set. Okay. And this, let's say this is in vertex 1, vertex 2, vertex 3, and this is vertex 4. But now 4, if I connected to all 3 of these things and I took everything, I get like a tetrahedron or maybe the interior of a tetrahedron, whatever. But I'm not doing that. I'm going to take this edge, and this edge. Okay, I'm not filling in the other triangles in the tetrahedron. Okay, so this is delta is given as this picture. Okay, so what we have to do is just make sure we understand what that means. What are the faces of this? Well, we could look at the so actually, what's the smallest? What are the smallest faces of this? Yep.
1, 2, 4.
1 is a subset. 2 is, 3 is, 4 is. Exactly, except those aren't the smallest ones. And the reason I'm saying this is because if you ever really do simplicial complexes, you have to always keep track of that you have this. In fact, you have then two different, very different trivial complexes. I think one's called, I don't know what they're called, but anyway, one of them is just the empty set, and the other one is where the set delta is the empty set. There are none at all. So those are actually different. What?
One's the void complex and the empty complex?
Yeah, that's right. So the void is where delta itself is empty, and when it has just this one, it's empty. Okay, so that's maybe a bad sign. Okay, what about the these are all the atoms in it somehow. Okay, and they don't all have to be in there. Like if I had 5 and 6, we would leave those out of this. Okay, what about edges? Yeah, we have all, there are 6 edges between these things. We have all edges. IJ. I don't want to write all 6 of them out. And what about triangles? So remember, the way this works is that you always get, whenever you have a set, you always have all the smaller ones. So it's always going to be these simplicial kind of things where you have triangles and tetrahedra and so on. So what are the triangles in it? 1, 2, 3. Okay, this is all the faces. Okay, and now I'm going to move back over to here. So we need to change that. Okay. So definition, the Stanley-Reisner ideal. So, or the ring also. Of delta, which is a simplicial complex. Okay, so on, let's say on the set 1 to n, although it doesn't have to be on that, it could be on any set, but let's just leave it like this. So k of delta, this is the notation for the ring, and this is going to equal k of one variable for each one of these things and labeled as whatever you want them to be, but we'll use x1 to xn. And it's modulo some ideal, which is going to be I delta. And I delta is the Stanley-Reisner ideal. Is the ideal generated by the monomials corresponding to what? Okay, one can imagine a couple options. So what actually, if you're actually giving one of these things, one way to generate it is to give the maximal faces only. Because all the other stuff, once you have 1, 2, 3 in it, and actually we have, so this is a maximal face. It's not contained in any more. And this is also maximal. It's not contained in any other one. So you want to maybe give the maximal. What?
Or it's not contained in the edges.
Yeah, no, you're absolutely right. That's the trouble with not writing these things down, because in fact, what you have is 1, 4, 2, 4. I should have just written them all down. That was really stupid not to. 3, 4 these are maximal faces. Geometrically, you can see it. I mean, the maximal face is this, and then these things aren't contained in any other face. So that's just it. Okay. So let me do that. Now, so what should the ideal I delta be? Monomials corresponding to all non-faces of delta. You can't say, you can't have it be generated by all those faces because you want it to be an ideal. So if I take xi times something, that's going to make a larger thing, and that's not the case. But if I have something that's a non-face, certainly anything larger will also be a non-face. So xi times it. So let's actually write this down. So in the example, I delta is equal to what? What are the, we not want all the non-faces. So maybe before writing that, what are the non-faces? Actually, there aren't that many non-faces. Yep. Sorry, what are they?
1, 2, 4, 1, 4, 3, and then 2, 4, 3. Weird way to put it.
It is a little weird, but whatever. Okay. So anyway, those are the only 3 non-face. Actually, no, there's one more non-face.
1, 2, 3, 4.
Yeah, 1, 2, 3, 4. But the thing is that so the I delta is going to be given by all of these monomials. Like for instance, this one is going to become x1, x2, and x4. But if I multiply this by x3, I get this. So really, I only need to all, if I really want to, I can do here minimal non-faces. This is a fit of non-face, but it's not minimal in all of them. But anyway, so I have this one, I have x1. If you don't mind, I'm going to do it in order now. x1, x3, x4, and then also x2, x3, and x4. Okay. So this is generated by by the monomials corresponding to the minimal non-faces. I think the hardest part about the whole simplicial complex theory is coming to grips with this having to deal with minimal non-faces, maximal faces, but it's worse than that because, as we'll see in a little while, you also have maximal cofaces and minimal and things like that. Okay, non-cofaces. But right now we're not going to worry about that. So one thing I do want to remark on here. So notice that this is a square-free monomial ideal. So it's a monomial ideal that is radical, and so note one is that I delta is a square-free, is a radical monomial ideal. Okay. Also, that any radical ideal, any square-free monomial ideal, J is I delta for a uniquely determined delta. Okay, you all see that right off the bat. Basically, if I have a square-free monomial ideal like that, that's telling me the minimal non-faces. That means if I remove any variable from it, I have a face. Yes, in all of this, I am dealing. Normally, this is yeah. So let's say on a finite vertex set, it is the case that you could do this for infinite things, but computationally, we can't really deal with that so well. So maybe we could, but anyway, we're not. We're doing the finite ones. It's still the case probably, even if it's infinite, but I haven't really thought about that at all. So okay, so this is kind of cool. That means that if you want to think about square-free monomial ideals, that's equivalent to thinking about simplicial complexes, which gives you a way of visualizing things and understanding things in perhaps a better way. So now our next goal is to find the primary decomposition of I delta given simplicial complex. Okay, remember what it looks like. I delta is equal, since it's a radical ideal, it's just the intersection of a bunch of prime ideals. And P sub I are equal to monomial prime ideals. Which are just sets of variables, are generated by sets of variables. So it should not be so hard, except it is. I mean, if you actually think complexity computationally, finding these things, well, that's not quite a well-defined thing as far as complexity class goes, but you can say that it's not in NP, okay, or it is in NP. It's not in P, probably. Okay. Let's see. Yeah, let's move over to here. Yeah, it is NP hard, I think, if I define it correctly. What is NP hard is essentially to figure out what the codimension of this of a monomial ideal like this is, and you can, since you can get that from this information, that's already tough. Yeah, that NP hard is the right phrase. Okay. So the question is, even in this example, how would you do it? Well, we know how to do these things now, right? We can do the irreducible decomposition of it by just splitting it up as many ways as we can, and you can actually write that down for that example. Maybe we should do, but for the moment, you know, it's whatever it is. Did I actually figure it out? I think we could actually do it. They all have an x4 in it right there. So it's going to be the ideal x4 intersect with something involving 1, 2, and 3. And sure enough, let's see, in our example, I delta is equal to the ideal x4 intersected with, and what's left is the 1, 2, 1, 3, and 2, 3, which are sort of like 3 lines or 3 something or others. And so that's going to be the ideal x1, x2, x1, x3, and x2, x3. Sound okay? So if you think about it, that really is what this picture is. Though that this says that the components of the zero set of this, right? The zeros of this are the union of these 4 zero sets. And you can almost see them all right away. Which one does x4 correspond to? It corresponds to the vertex. That's not quite, it does sort of, but not in the way of the geometry. This is not a component of the, so if I look at the zero set of this thing, here I'm going to get the union of 4 things. And so, but the 4 is one of them somehow, but it's not exactly what that is. So what is that corresponding to? It's actually x4 equals 0, which means that it's sort of this this plane down here, or the 3 space, if you are thinking somehow. So x4 equals 0 is this guy here. And what about the other ones? x1, x2? x1, x2 is 0. So that's the line 3, 4. So there's always this flipping of things. You know, you start with 1, 2, and you end up with 3, 4. You start with 4, you end up with 1, 2, 3. And that is, in fact, what we're going to do. We need the definition now. A coface. I don't know if I should put a little dash in there or not, so that someone doesn't pronounce it coface or something like that. But at any rate, a coface of delta is the complement of a face. Okay. And in this case, it basically tells you what the, you know, well, the ideals tell you what the components are too, but then this sort of tells you what the axes are, you know, that are part of that. So for instance, as an example, in our running example here, so if I take the set 1, 2, this is contained in delta is a face. So the corresponding complement of a face, so the corresponding coface is 3, 4. It's just a complement in V of that set. So the idea is that we would like to understand what these things look like in general. And I want to give you a theorem now. that we will actually prove. We will not prove everything today, but this one we will. This stuff here is what I'm erasing right now is what we're going to be using. And I should have said that before I erased it, but I already half erased it. So the theorem is, let's let delta be a simplicial complex. You know, in some ways, what we should do, what time is it? No, I want to actually do this now, but really what we should do is take a few examples of these things and see what we get. But we have one example at least, okay? So here what I want to say is then I delta is equal to the intersection over some sets tau, which I'm not going to say anything about yet, of the set xi such that I is in tau, is a primary decomposition of I delta. Okay. Now the question is, what subsets of taus do we take? Ah, are they? So yeah, so it seems natural that since I just had the definition of coface up there, that might be it. But in fact, if you think about it, let's see, what about these x4, x1, x2, and so on? Is x4 a face of delta? X4 is the ideal of it is giving you the face 1, 2, 3. So it's somehow the complement of that. Yep.
Cofaces of the maximal faces.
Yes. So it's tau is equal to a minimal. The reason I'm laughing is because I have to translate between minimal coface and so this is minimal coface of delta. Okay. So the minimal cofaces of delta, well, that's going to be the maximal faces, right? So the maximal faces, we have 4 of them. No, we don't. Yes, we do. We've written down 4 maximal faces. So we take the complements of each of those sets. Here we get 4. Here we get 2, 3. Here we get 1, 3. Here we get 1, 2. And that's exactly what we have up there. Okay. So this is a kind of a cool fact that we have here. But let's prove it. So the main idea in order to prove it, actually, how would you prove such a thing? Any suggestions? Well, if you've done any simplicial complexes, you might actually use this fact just all over the place, but kind of forget to do it. By induction, that would be one option. That might work. Actually, there's probably a lot of ways of proving this.
You've kind of drawn that.
It's really in 4 dimensions, but in fact, actually, you can treat it as looking at, you can slice the 4 dimensions with the hyperplane where the sum of the xi's is equal to 1, and then the resulting thing will essentially be this picture. Essentially. But it is true that this probably should be drawn as such in 4 dimensions. But you know, in one way, this is also a homogeneous ideal. So we could look at the 0 set in projective space if we really wanted to, and then it would be more like that picture. But that's anyway. Let's see. But there's a way of using the primary decomposition facts to prove this, and I think it's a very straightforward proof. Let's see if you agree, and that gives it to you directly. Okay, so the idea is to use that each P sub I, so this is in if I delta is equal to P1 intersect to PR, that each P sub I is an associated prime. i.e. that that Pi will equal I delta colon some F I, or is the radical of I delta colon Fi. Let's just say F, it'll be each Pi will have a different one. Yep.
Sorry, going back to the statement, what is xi here? Is that a monomial or is this a set of variables?
Sorry, that's a good question. This is in the ring R, join x1 to xn. And I should really say this is on V, which is the set 1 to n.
But
Okay.
this is saying each of these ideals in the intersection, this is generated by some collection of single variables, right? It's
So
not
for
monomial.
instance, let's as an example, no, you're right. So if tau is equal to the set, if tau is equal to the set 1, 2, for instance, this ideal would be the ideal x1 comma x2. Okay, not x1 times x2.
Yeah, okay.
Okay, so it's otherwise I would have had to put product of xi and I and tau, which actually is something else we will do. But in any case, not quite in the setting though. So so I want to, let's see, that in this, I guess we now move over here, so we have to, you already did it, man, way ahead of me. Okay, so
Well, you were jumping back and forth between these.
oh, I see. Okay, that's true. So what we want to do is, I guess, the question is we have to prove inclusion. I kind of forget my proof here. I have to just think about it for a second. So whatever ideals are going to be over here have to satisfy this kind of thing. And then we have to, whatever we have, that we have to make sure that there's nothing else in there except the stuff that's in here. And so let's see if I can remember how this goes. So suppose, so this is proof. We already started proof. This is a continuation of the proof. So suppose sigma is, say, J1 to Jm is a maximal phase of delta. Okay. Then, if I take a look at the set J1 to Jm and K, this is a minimal non-phase for all K not in sigma. So it's certainly a non-phase. And actually, is it a minimal non-phase? The non-phase, at least. Well, in any case, let's see if it matters. So I delta colon xj1 to xj sub m is equal to what? So forget the minimal. It might, I think it's possible that like Jm time and K could be a minimal non-phase.
Look at the example. Take sigma to be the face,
1, 2, 3, yeah,
and then imagine that we delete an edge, say 1, 4,
yeah.
and then drop 1 from the set, but throw in 4. We're getting 2, 3, 4.
We have a maximal phase 1, 2, 3, and then I add in 4. That's going to be, that is not, I guess that is a minimal non-phase.
I also
but-
wanted to delete one of the edges because
A itself could be a face, like in your example, and then.
Yeah, that's right. K is a face, and so a minimal, but that's a face then. So, but I think it's still the case that if I take K and any, if these were completely disjoint, for instance, well, no, then
Just suppose under subset, so if A is a non-phase, then this is not a minimal non-phase.
that's right. That's right. Okay, but nonetheless, this thing here is going to be the set of xk's where K is not in sigma. Right? Because each one of these things is a non-phase. And if I take any other variable in there, that would be a variable in the face. And if that's in the ideal, then since it's radical, that thing would be in the ideal, which means it's a non-phase. I don't think I need minimal non-phase in here at all. I'm not sure. Well, actually, I do. What I'm really using is that this, yeah, this is not this. Let's get rid of this before it's unfortunately on to date now on recording, but I think it's just a non-phase. What we are using though is the fact that it's a maximal phase. Okay, so so now what is this though? This is equal to the set just like that. This is xk, where k is in k is in V minus sigma. So this is a cophase. This is equal to tau is a cophase. And since that was a maximal phase, this is a minimal cophase. Okay. So what we've just shown is the following. Therefore, I delta is contained in the intersection of the xk's where k is in tau and tau is equal to a minimal cophase. Minimal cophase of delta. Because it's in certainly I delta is in each one of these things, so it's in the intersection of these things. So this direction then, okay, so this shows this direction. The other direction, I think I have written down just take a square free monomial in the right-hand side. Okay. The corresponding subset has to be a non-phase because it's in this. I mean, corresponding subset. So this is to be, I want you to, this is going to be confusing, so it's better to think about it. Take a square free monomial. In the right-hand side. Is this guy here. Okay. The corresponding subset, which is just the support of that square free monomial, the corresponding subset. If you think about it, if I take something that's in any one of these things, it has an element outside of every maximal phase. So the corresponding subset is not a phase of delta. The corresponding subset is not a phase, therefore it is a cophase. But we've already gotten all the cophases essentially in here. So I'm going to say, anyway, it's a cophase. No, sorry, not a cophase. No. I'm getting screwed up here in my. The corresponding subset is not a phase. Therefore, it is in I delta. right? Because this is the ideal of all non-faces. All monomials corresponding to all non-faces. And so the key thing is, if I take one of these guys, then I only have to look at square-free monomials because I can tell if a monomial is in there or not by just looking at support. Then I have to really check this statement here. The corresponding subset is not a face. But I think that's because if I have an element in this intersection, suppose it isn't a face. Well, these are maximal faces. So I take a look at one of them. If I take a look at my face, I look at some maximal face that it's in, and then this is basically saying, no, I'm sorry, it's not in that maximal face. So it's not in any of the maximal faces, therefore it's a non-face. And not a face. Okay, so anyway, I thought overall there's a couple little things. This kind of reasoning is always what you have to come to grips with in this kind of game, but that proves that this is the primary decomposition. Now one might ask, how do you actually do that? However, it is now time. I would like to do that next, but in fact, I think let's make sure that the problems I gave here. Okay, I didn't define Alexander dual yet, which is some part of problem 1. Problem 2 doesn't use Alexander dual. So, and problem 3 uses non-square free monomial ideals, which we haven't done yet. So I think what would be good to do is to spend time doing problem 1, except just ignore the Alexander dual part of it, and instead do the rest of that problem. And then problem 2 is something that's going to be useful for the primary decomposition in general that we're doing. It's this notion of algebraically independent sets, which is, by the way, an interesting simplicial complex. And in fact, there are people that are here that are working on understanding these simplicial complexes for arbitrary ideals and things like that. But we're just going to mostly the problem 2, well, after the first 2 parts, is basically just trying to understand what this simplicial complex is for a monomial ideal. Okay, so why don't we take a 10-minute break? It's 11:08, and then people can start working on some of these things. You can do the other ones too, and if you want, but we will talk about the Alexander dual, but after break, I think, after project time. Yep. In
problem 1, you've given us some Macaulay 2 code. I assume that's giving us the list of edges of the graph.
So this is so I gave you just a little to get you started on it. So for instance, there's a package in Macaulay 2 called naughty graphs. I think we might have used that previously at something, but I don't know if we did or not. And it's nauty, not, naughty, as it were. And but what's cool about this is it generates all graphs of small size and really does it quite well and very fast, up to isomorphism. And so this generates graphs of, this is of 6 vertices and minimum degree is 2. That's just to get rid of, just to make it a smaller set. And then I just grabbed one, and then I showed you a couple ways of getting the edges and stuff like that. If you just do edges of the graph, so those generate graphs doesn't actually give you graphs. It gives you these very encoded, weird encoded strings. Naughty has some very compact way of describing these things in terms of these strings. And this function takes that string and makes a graph object out of it in Macaulay 2. And then you can get edges, and then you can use that to make the ideal of the edge ideal. And then the idea is, what does it look like? I mean, you can actually think of that. One thing I didn't write down, an edge ideal is coming from a graph, but that is not the simplicial complex. So what is the simplicial complex, and so on. So anyway, that's what that's about. The Alexander dual, yeah, it would be nice if we had gotten to that, but we will. But there's plenty to do here. Anyway, in fact, maybe it's better to not have done it yet.
So the single slash means apply a function to a list.
Yeah, so if you have a list slash a function, the single slash means apply it to every element of the list and give the result of the answers.
And then with the double slash.
Double slash is, I think of this as a way of piping through information. You have a list, a single slash applies the function to every element of the list, making a new one. A double slash applies that function to the entire list. So in other words, sort of it is before that you're getting a list of pairs of things that are edges, and now slash sort is just sorting them so that they'll be in some reasonable order. It's not necessary at all.
Is
but-
that equivalent to saying on the second last line, run the second last line and then take sort of that?
Yep,
So
exactly.
it's
It's exactly the same. I just get kind of
But then you have to put parentheses in, and you know when you start writing the line, you have to know that you want to sort first.
or you have to search, you go back and put it
Yeah.
in and things like that. Yeah. So I
I can see why
I kind of like this notation. Not everyone does, and if you
Okay.
don't, that's totally cool.
Then it's
but-
not helpful. I use it all the time.
Yeah. And the tree ideal one is you could actually do part A and part B without the Alexander dual. Actually, the interesting one is why they are called tree ideals. I don't actually, I have to go back and think about why that is also, but it's kind of interesting. Each standard monomial, a standard monomial is just a monomial not in the ideal, corresponds to a labeled tree. So that's why, that's an interesting problem also from a combinatorial point of view. Anyway, so in 10 minutes, we can come back and work on that stuff.
So what's the?
So let's see, what time is it? It is 11:22. So how about we work on this for, is a half hour a good amount of time, or do you want more, 45 minutes? We can always decide a little bit later when you start taking a look at it. But then I do want to go through some of these problems and see what you have to say about it. And then we'll move on to Alexander dual stuff. Should we get back and talk together now? How did everyone? Okay, I'll get this. Yes,
So I can sort of see when you're doing the primary decomposition of one of these edge ideal things.
Yeah.
You're basically saying, okay, you've got a whole bunch of edges and you want to make a collection of ideals so that the generators of the ideals tells you you've got at least one of these. So it's like these are edge. Yeah, these are vertex covers essentially, right? So is it really just the primary decomposition is the ideals of all vertex covers?
It's
really related to vertex covers.
so yeah, so like in this kind of statement here.
Yeah.
The I delta should be equal to the intercept. So there's two things going on here. First of all, what is the simplicial complex that I delta that this edge ideal is a complex of?
I think we were just trying to make the decomposition from scratch without associating it to a complex first.
Yeah, okay. But if you do that, you'll see that the graph is a simplicial
Yeah.
complex, but that's not the simplicial complex of this thing. And instead, this is a simplicial complex of another set, which is essentially the vertex covers of that set. So, and then that's why if you're taking if you take a maximal vertex cover, minimal vertex cover is just going to be in there too, but it will be redundant, right? Because it's a larger ideal than that. But if you take so a vertex cover is just a bunch of vertices so that every edge is in one of them. So that means, in fact, that it is a prime that is larger than the ideal. So it's one of, and it might not be a minimal prime, because if there's a smaller set that does it, well, that's also a vertex cover. So the minimal vertex covers are going to somehow be the minimal primes of this thing. But a minimal vertex cover is corresponding. No, wait a second, I got it wrong. Sorry. It's confusing. So, so a vertex so this is saying basically, this isn't saying, I mean, we're not doing it this way. So, but if you have a vertex cover, so suppose I take, oh, no, a minimal vertex cover is still large enough. That, no, I'm sorry. Those are the one you want, it is the intersection minimal over minimal vertex covers.
Is, when you use Macaulay 2 to just get like primary decomposition, how unique is that result compared to like, if I was like trying to make this from scratch, like, is that gonna agree with if I just?
So for a monomial ideal, if it's a prime monomial ideal, and not prime, a radical monomial ideal, a square free, then it is absolutely unique up to order. There's no choice whatsoever. If it's a monomial order, if it has embedded primes, it can be not unique. There is still, I think, a canonical one that works, and it's giving you that one. But we can maybe
So if we
talk
like
about
trying
that.
to do this by hand, just like thinking about the minimal vertex covers and coming up with the primary decomposition, it will or should agree with what you get from Macaulay 2, just straight up. Like,
Yeah,
yeah.
absolutely.
Cool.
Because for these things, it's just a unique answer. How about anyone else? Which ones did you guys work on? The first one? Okay. So should we talk about it now? Okay, good. So so the first one is writing a function in Macaulay 2. Did anyone do that? Did you guys do it? You tried it. Can you link up by Zoom and show us your
Yep, I can do that, or I can try.
Can we make that Zoom window bigger?
Yeah.
Because I don't think we'll be able to see it.
I agree with that. First of all, we have to get rid of this. Is this the
If we just hit the rectangle on the top right of that window. Oh. Maximize maybe? Perfect.
okay, and now if you share your screen, which hopefully you can share.
I don't think Ilya's on yet.
How do I connect to the Zoom? I'm sorry, I've never done that.
Oh, that's right. There's a password that we have
You got
to
it
know.
sent to your email if you've registered for the course
Uh-oh.
a couple weeks ago.
I can find it.
But how do I get to the, like, where's the Zoom link itself?
It's at the,
Oh, okay.
yeah.
Updated Zoom link, thank you. And I've got passcode there.
I wonder if we should put the, maybe we can see it over there.
You've showed your code on there before. It's been fine.
Okay, I think I'm in.
Okay,
Oh, I'm gonna mute myself.
yes, good
Okay.
idea.
And then I'm gonna share my screen.
Here, you want to mute yourself, but you don't want to really mute yourself. So here.
Why is it not allowing me to share my screen? Use operating system settings, yes.
Oh, I see.
Wow. My browser has prevented access to your share screen. Firefox, why are you doing this?
Oh, wait, oops, I didn't want to share screen. So you can't do it, right?
I can't do it,
Okay,
but I could write on the board what it is.
yeah, let's do that.
Okay.
Actually, that's not so, such an awful way of doing it anyway.
My browser, Firefox, I think is a little bit too precious with my security.
Your camera is still on, but.
Oh, my.
Here, since you're gonna take this and
Okay, so
you can just put this in a pocket or something like that.
there's good, I think, I hope. And then you can go in my pocket. Okay, hopefully everything is good. Okay, so to start with, there was the code that you already had up, which is basically the output from that
gives us some graph G is a graph. And then there was another piece of code that you gave us that was just edges G, and then toList, I think this capital toList, and then /sort. What this one does is it just makes the edges which come out of the function a little bit weird, but then when you sort, everything sort of gets put into one nice list, and then when you sort again, now all of a sudden it is in like quote unquote alphabetical order. So this is an important piece, and so I created a function edge ideal. And what this function eats is a graph G, and it spits it to a whole bunch of stuff. So the first thing that I did was create an edge set. So EG is equal to, I'm going to call this guy star. So EG is equal to star. And then what I wanted to do was count the number of distinct vertices within this edge set. And so I am counting that with n is equal to pound, and then that pound is going to eat set flatten, and then we're going to eat EG. So the EG spits out the edge set, then the flatten turns that into just so the EG is a list of lists. This just turns it into a single list. And then set deletes all of the duplicates, and then pound tells you how many distinct elements there are. And then I did some text stuff, basically saying print in the ring generated by, and then so I'm going to do quotation marks to say that there's some text here, and then print in the ring generated by R is equal to QQ X underscore 0 to X underscore n minus 1. So here's my ring R, and then again we're printing print gens of R. So this tells you in the ring generated by all the generators of R, so cool. And then there's some more text that basically just says the ideal of the graph with edges, and then I print out the edge set. So print EG. And then the last thing is, and then I just say again, so the ideal of the graph with edges EG is, and then we just make the ideal, I is equal to ideal, ideal, apply, and then we're eating each thing in the edge set, EG, and we're going to send that to, so I gets sent to X underscore I, or sorry, little I, pound 0 times, almost there, X underscore I pound 1. And then that closes everything, and then you run that and a function closes, and you feed it a graph, and everything's good. Cool.
And now I will show you a couple things that one can maybe
Do better.
just a few things about the Macaulay 2. Okay, so that was awesome. So now there's a few things though that when you have these, this is just Macaulay 2 straight away. I mean, this works fine and everything. I would generally put a colon equals on these to make it a local variable. Otherwise, if someone else has an EG out there somewhere, it will write over it. And it will be really confusing for anyone using it, including yourself. Same with N, same with R. Okay. This one's a little tricky because over here, I'll say something about that in a bit. This set and flat, I believe you can do number sharp sign vertices of G also. So So here, let me just do that in a different color. So number of vertices of G should work too. And you could put parentheses around it or not. It's really not relevant for a single thing. R colon equals Q of x underscore 0 to x underscore that. That's good. Oh yeah, that's another thing. Inside of a function, you can't you need semicolons at the ends of these lines. So that one is fine there, but you need that, and then there and here. I'm not going to worry about the print things, although that's a lowercase print, not a capital print. Okay. This is yeah, there's an I here for ideal. And apply e.g. I would probably call that E or something like that rather than I, but this is all fine. Now there is one little problem, especially if you're writing inside of a package in Macaulay 2. Variable names are the hardest thing in Macaulay 2. It's really because we want to make it very mathematical so that you can use them and so on. But if you are writing a package and you did this, it would wipe out anyone else's x's that they had before. So one way you can do it over here is x underscore that. This is an integer, right? Zero, I mean, the vertices of G are 0, 1, 2, and so on. And this will give you x underscore that will give you this one. You can also do r underscore that. And then you don't have to know what the variable name is. So if I do r underscore I sharp sign 0, this could be also I underscore 0. So sharp sign and underscore are both indexing operations because we can't use brackets. This one is a programming one. This is a mathematical one. Programming one is fine for a list because it's a list. It's taking the 0th element of the list. So if this I were equal to if I were equal to 3, 4, which is very much likely what one of these edges will look like, then I sharp 0 will be 3. I sharp 1 will be 4, and this will be R underscore 3, and it would look on 0 based, it would look for the correct variable here, and that's what it would be. So that's kind of useful if you're writing in a program to be able to do that. But otherwise, this all looks good. I would probably call this lowercase edge ideal, and the reason I would is because in Macaulay 2, it's more idiomatic that functions almost always, except for a couple names way early on, it starts with the lowercase letter, and then it's camel case. Each one becomes capital after that.
What is the reason of this?
Just to make it so that you know what kind of things are. So functions are like that. Types are usually, this would look like a type. Or also optional arguments are given with this kind of capital things usually. You know, it's not enforced, so you don't have to do that. You can do Greek letters, by the way. You can use Unicode. So I don't know if you've tried it yet on Jupyter, but I don't actually know how to do it in Jupyter. But in VS Code, you just can start doing \alpha, and it will give you an alpha and things like that. And Emacs does that too, but you have to set something first to do it. Yeah. Yeah. Question?
Kieran just started doing Japanese in Macaulay too.
But I guess you're Unicode, right?
Oh, yeah,
whatever
yeah.
variable names you want.
Did it work?
Oh no, I haven't actually tried. I was just writing on my thing. Actually, well, you could try it if you did a Unicode.
I don't, yeah.
Okay, so anyway, that's part A. Okay, so this is kind of a pretty good function in the sense that if you ever have some set of ideals that you are trying to investigate, this is the first step of you want to be able to do this, make it so that, first of all, then you shouldn't just use it. You got to look at it and make sure that it's giving you what you think on a few examples. And in fact, there's ways of making tests and things like that. If anyone's interested, we can go over stuff like that at some point. That's actually probably a worthwhile thing to do. And because then when you go back later, after not working on it for a while, you can run all those tests and say, oh yeah, this function's okay, I can use it, rather than not being sure if it's even giving you what you think you're getting from it, which would be bad. Especially if it's complicated, that could easily happen. So that's part one. So how about part two? Take a specific one of these things and compute its primary decomposition. Did anyone do an example of one of those things? Which example did you do?
5-cycle with a couple extra edges.
Okay, 5-cycle. Can I write down a pentagon?
Yeah.
1, 2, 3, 4, 5. And let's call this what, 0, 1, 2, 3, 4?
Sure.
And it's going to be a cycle. And then there's going to be other edges, right?
Say 0 and with a vertex on that board.
Oh, there's another one here. So that's 5. And it's this and then this. Okay, cool. Okay. So should we write down what the ideal is? So the good thing about edge ideals is that they are very easy to write down. But the trouble with them is that you think it's just a graph, but oftentimes you think of it also as a simplicial complex, which is this other thing, which is not the graph. And that sometimes makes much more sense than the edge ideal. So it's tricky. I mean, you can say a lot of things about it, and a number of people here, Adam especially, he's probably the man, the edge ideal man. See here? No. There's another such. But anyway, okay, so what is the ideal here? It's x0, x1. I just have to do it for every edge, right? So let's do it x1, x2, x2, x3, x3, x4, x0, x5, x4, x0, x5, and x0, x. How about not? Ouch. X2, x5, right? By the way, what's the codimension of that ideal? You just want the minimal set of variables that that this ideal, that the codimension is going to be this, the size of the smallest minimal prime, basically, or the.
Oh, well, 3 in that case, I guess.
So what variables work? X0?
0, 4, 5, and 3, 4, 5.
So these are two minimal primes of this. Let's just check. X0. Wait, this x1, x2 doesn't have anything. Maybe your indexing is different than mine.
Oh, I'm just working with a different graph. Never mind.
Yeah. So we'll have to figure that out. But anyway, we want to calculate the minimal, primary decomposition of this. We could try to do it using that and looking at, but then we have to understand what the simplicial complex is. So I think probably a little easier right at the moment is not to do that, but to just split this up like we have been doing before. So let's I mean, obviously, what we could do first is type it into Macaulay 2 and see what it gives you. Okay, but like I could split. Here I have I, which is the whole thing, IG, and now I can do this side. I could take I colon one of the variables. I don't have to take infinity, and then I could take I. Actually, I could also do it is I add. Well, let's do it this way, and then I comma x0. Okay. So what are these things? I colon x0 gives us x1, x0, no, x1, x4, x5, because those are all the edges to the x0. And then what else? It's probably all the edges of the graph that doesn't involve 0, right? When you get rid of it. So it's, what is it? x2, x3. And x2, x5. Oh, no, we've already got the. Oh, I see. We're getting rid of the entire so-called link of that thing. And then we're looking at it. So that's this ideal. And then what is I comma x0? So then we just get rid of the 3 equations with the x0 in it. So here we have x0, and then we have x1, x2, x2, x3, x3, x4. Not the x2, not the x2, and then x2, x5. Okay. These are both edge ideals, again, where except for these x0s. So you have to think about what that would mean edge ideal wise. But it doesn't really matter because it's just a variable going along for the ride and so on. This one, what's the primary decomposition of this one? Exactly. Okay. We actually did that when we were doing the irreducible decomposition thing. You take an element and you can actually break it up into two parts. We could have done that up here as well. That would mean that we add x0 and then add x1. We didn't do that. I did it this way instead. Okay. And this one, I guess we can also break it up, or we can do the colon thing. Which one? How about colon? Which one has the most stuff in it? One appears only in one thing, two appears in three things. So I think that putting two in is a good bet. So if I do this thing, if I do colon x2, what do I get? I get x0, I get x1, I get x3, I get x5, and but the 3, 4 is already in the ideal. So that's actually a pretty good one. That's already there. And then what do I get here? I add x2 in, and now I get x0, x2, and now I get x3, x4. And this splits up into two, just like that one did over there. That's x0, x2, x3, and x0, x2, x4. So actually, it's the intersection of these 5 things. Can someone type in this ideal into Macaulay 2 and just see if we did this correctly?
I can try.
But in any case, notice what these things are codimension 4. So, and how many variables are we in? We're in six variables, right? So affine 6 space. So these are each dimension 2 zero sets if we do it using our usual algebraic geometry. And this one is 2. So those 3 are that, but these are higher dimension. So these are the 2 primes of highest dimension, which are the minimal primes. Just to screw everyone up. So, so a minimal prime, the zero set of a minimal prime is the highest dimensional components of the thing. It really comes about because people were doing this in commutative algebra or versus in algebraic geometry. And the question is, it's minimal in commutative algebra because you're using the sort of contravariant category somehow, and the other one you're using the other category. Okay, anyway, so these are these. What do these things represent up here?
Part C asks us to look at vertex numbers.
Actually, are all of these distinct? I think that they have to be the way I've done it. Okay. But you have, depending on how you organize this, you have to be very careful. You might get lots of redundancy. For monomial ideals, it's a little easier to avoid redundancy. Otherwise, it's actually a serious problem.
Are the dimension 2 primes, are they minimal primes?
Yes. So, actually, are they? They should be. Every ideal that appears in here should be a minimal prime.
Because they're not contained.
They're not contained in one of those. Okay. Because those have x0 only, and this doesn't. This one does have it, but it doesn't have the other one. So these are all minimal primes, even though these are larger. That happens all the time. Okay. So the zero set of this whole ideal, if you think of it in 6-dimensional space, is the zero set of all 5 of these things together. And now combinatorially, what is it? So let's do one of them. So let's take 0, 1, 3, 5. 0, 1, 3, 5. Bunch of vertices. And yeah, you're right. Okay, so that hint might have been like, you know, a little bit of a hint, but you didn't have that much time to think about it, so I wanted to sort of make sure. So what does a vertex cover?
It's a subset of the vertices such that if you take any vertex, it's adjacent to one in your set.
Yeah, it's a vertex cover, as was said, which people can't hear online, is it's a set of vertices such that every edge contains at least one of the two, but possibly two or more. So one vertex cover would be all of the vertices, but we're probably interested in the minimal vertex covers. And this is the idea is that these should be the minimal vertex covers of the study. So does that look right? It seems absolutely fine. I mean, certainly if I have a vertex cover, by definition, that means it's going to be an ideal essentially containing that, because for every edge, either one of the two has to be in the ideal. And so any prime that is larger than the ideal I sub G has to give you any prime ideal with just variables has to be a vertex cover. And then the minimal primes are the minimal vertex covers, which is what these are. So that's good. So primary decomposition, minimal primes. So primary decomposition and minimal primes are exactly the same information for a square free monomial ideal. No problem there. That was almost there just to make sure that you thought that through a little bit.
I can confirm also that that is indeed the primary decomposition.
Awesome. Okay. So did anyone get to problem 2? You did only problem 2. I think what would be good, I would like to go over that, but maybe you could do that next week at the very beginning or something like that, when other people have had a chance to look at it. Okay, so please look at that for next time. And what we'll do now maybe is in the remaining time, I want to do the Alexander dual stuff and then maybe start the dimension 0 part. Okay, cool. Any questions online at all? Anyone there online?
No questions
hard to tell.
whatsoever.
All is good?
Yep.
Okay, awesome. Okay, so so there is this notion. Oops, let's see. Where do I want to start? Let me let's start over here. Okay, there's the Alexander dual of a simplicial complex. And it has a very simple definition, and yet it's a very confusing definition at first, okay? So I have to tell you what the set of subsets is. Okay, delta of a simplicial complex delta. And I have a set of vertices 1 to n or 0 to n minus 1 or something like that. I don't really care, but it's a finite number of vertices. And now I'm taking this thing here. Actually, to tell you the truth, for all of these things, I need finite number because we're taking complements. And if I take a complement in an infinite set, that's not going to give me a, actually, maybe it could, but yeah, finite, okay? So this is the set of all F's, which these are going to be subsets of V of the thing, such that the complement of it is not in delta. So where here FC is of course just the set of the vertices. Let's do this as 1 to n. Say this is just 1 to n set minus F. Okay, so this is this thing. Okay, so as an example, I think it's really good. This stuff you have to keep grounded on examples. Otherwise, it's just you're just throwing symbols. You might prove what you want. Who knows if you're not doing examples. Okay, so so remember here, delta was given by what were the maximal faces of delta in our example? That was 1, 2, 3 was one maximal face. 1, 4, 2, 4, and 3, 4. Okay, so this is in our example that we had first. Okay, now what I want are what is delta? What is in here? So what are faces in this? So I want to take the faces that are the things that are non-faces and then complement them. So what are the non-faces again? I think we wrote that down as well. Maybe I should write that down first here. So the non-faces of delta are what? Almost everything in the face except the four things that we had before. The triangles involving 4 and then the whole tetrahedron. So the non-faces are going to be 1, 2, 4, 1, 3, 4, and 1 and 2, 3, 4. Okay. And 1, 2, 3, 4. Okay. So where I'm being kind of glib about this, this means the set 1, 2, 4. Okay. So now we want the non-faces, and now we just take the complement of all those guys. That's pretty not so bad. So this thing is equal to the set of subsets, which is the complement of this guy. Yeah, that's right. It is 3. That's a set 3, right? And then what's the next one? The complement of this 1, 3, 4 is 2. And the complement of this is 1. And the complement of this is the empty set. We typically don't write that in because it's always in there. But in any case, this is a pretty trivial, these are the faces. What is this? This is 3 points. Okay, nothing else. So what's the ideal of this thing? So we want the minimal non-faces. So what are the minimal non-faces here? So it's actually going to be the ideal generated by the minimal non-faces. Remember, we're in 4 vertices 1 through 4. So x4, 4 is not a vertex. So that's a non-face. What are the other non-faces? Yeah, any edge in here, because the highest thing you have are points. So that's going to be x1, x2, x1, x3, and x2, x3. And of course, all the ones with 4, but they're already in there. Okay. And I believe once we have all the edges, we have all the 3 faces and higher. So this is everything. Okay. So if what was I delta again, by the way? It was the ideal of non-faces. That was x. Actually, what was the ideal of non-faces here? Does anyone have that down that I have it right here. It's no, I don't have it right here.
It's the ideal generated by the 3 non-faces there that aren't 1, 2.
Oh yeah, that's right. So it's x1, 2, 4. Oops, we don't have triple indices though. x1, x2, x4, x1, x3, x4, and x2, x3, x4, right? And that was it. What did we also say? We also said that this thing was equal to the intersection of the following primes. x4. What were the other ones?
x1, x2, x1, x3, x2, x3.
x2, x3. Let's just stare at this a little while. And there's a theorem, really useful theorem, staring us in the face here. So this is information. depending on how delta is given, one of these pieces of information might be hard to get and the other one is trivial. But let's suppose that it's easy to give this one and that this is hard to get. Okay. But we have it. But now if we come down and look at this ideal, looks to me like it matches 1 for 1 somehow. So in other words, this ideal here it should hopefully tell us exactly what this is. So so in fact, let's write that down as a theorem or a proposition. So proposition, I'll say I of this thing het is minimally generated. So that's these guys here. By the monomials now this, remember we were saying that we did the brackets last time. Now we're going to do the monomials m tau, which is going to be the product of I and tau of xi, where tau is a minimal coface. And this is the same indexing as the generators here is the same as the generators as these things, except that there's a way of going back and forth between them. So i.e., each generator of the dual of delta dual gives a minimal prime of I dual of I delta. Okay, and in fact all of them come this way. Okay, so this is a pretty cool fact. This is something that you can prove directly now, but you have to puzzle it, and I think it's really worthwhile puzzling it if you haven't done that. And it just gets confusing with all of these things. So let's try to unconfuse it just a little bit. Yeah.
Can I ask a question about the dual?
Yes.
So if I want to take the dual over graph, I sort of put a vertex on every face and then add edges crossing edges.
No, that's not quite this
I-
dual.
Sorry, that's not quite this dual.
No.
It feels like for the example that we've done, for some reason, like we have these triangles that aren't filled in the original complex, and I've sort of put a vertex on each of these.
Yes, that's true.
Is that just like a happy coincidence in this example, or is there a way to visualize it in this case? Or in general, sorry.
Yeah, I think you can visualize it that way. In fact, maybe what we're going to say right now will help do that. Might not. I personally find that I can easily get confused with this stuff. And so what I want to do is just here's a like a picture. It's not really a picture, it's a diagram. Suppose I have delta, okay? This is I have delta, and this is the set of faces. I can do two things. I can take two sets related to that. I'm going to put just arrows from here. So I'm starting with this, and one of them is I have the set of cofaces. I just take each one of these things and take its complement here. Okay, that's what a coface is. Or I could take the set of non-faces.
Sorry, is it possible to move the camera, please?
Oh, yes.
Okay.
Thank you. Okay, so we have the set of faces up here. That's just delta. Here we get the set of cofaces. Here we get the set of non-faces. And what goes here? This one here is taking F and going to F complement. This one's a little trickier. This is just taking the complement of delta itself. Okay, so so this is like the set of all subsets minus the sets there. And then here we also could say we can do the same thing. We could take these things and take their complements. The set of the non-faces. Okay, just for fun. Okay, so this is again taking an F here and going to the complement here. Or we could take the complement of all these sets, and I think we get to the same thing. Okay, you should check. Got it. You get to the same thing. Okay, so and which ones of these things are simplicial complexes? We have these set of all this stuff. This is a simplicial complex. So I'll say S complex. If I take the complement of things, do I get a simplicial complex? Absolutely not. I'm getting sort of like an order ideal is what it's called. Sort of the complements give you a different kind of object where once something is in it or not, I forget. Anyway, I don't want to go there. So, and this one, is this a simplicial complex? If I take all the other ones, absolutely not. This is not a simplicial complex. Now, how about if I come down here? This is, in fact, not only that, this is delta half. This is the Alexander dual down here. So you're doing these two operations here, and the confusing thing is that you're sort of there's a number of confusing things about it. Which way you go, you know, how you compute it, the fact that you're going through non-simplicial complexes to get there, that kind of thing. Okay. So this is the kind of thing, but these are dual. Clearly, if you take the Alexander dual of this thing, you go back because these are all interchangeable lines, in any case, also from the definition. Okay. So anyway, so that should when you think of it that way, you can think of minimal coface. Minimal coface, that's just a maximal. That's the complement maximal face. So minimal coface, but a minimal coface here, remember, these are going to, this is really confusing because what is, the generators of this are the non-faces of this thing. But what is a non-face of this thing? A non-face of this thing would be the faces of this thing. And then you take the complements of those. So play with it. And the good thing about that, trying to prove that, is it just gets you to come to grips with that if you've never done that before. Okay. Questions on that so far? The Alexander dual has lots of amazing properties. And how are we doing here? So the Alexander dual, if you take the free resolutions like we've done of the ideal I delta and I delta hat, it sort of, you know, we have these Betty tables. It almost transposes them. It doesn't transpose them, but what is transposed is the number of rows here becomes the number of columns on the other one, and the number of columns on one becomes the number of rows. It's really very cool. So there's all sorts of very interesting things along those lines. Okay, so now, but I want to, in the remaining bit, generalize this a little bit to monomial ideals, to not square-free monomial ideals. If we want minimal primes of a monomial ideal, any arbitrary one, that's easy. We just take the radical of it, getting rid of all the exponents, take that ideal, and just do what we've been doing. And so now we have that, but that doesn't tell you about the associated primes and you know anything else. So here, let's do general monomial ideals. Question?
Stupid joke.
Yes, sir. Okay. Okay, so let's suppose let's let I be now a monomial ideal. This is going to be given my generators M1 to MR contained inside of R, which is K of X1 to X R. By the way, for everything we're doing, the field is absolutely irrelevant. Everything's combinatorial that we've done so far, and it will remain so. But when you do free resolutions of these things, it's not dependent. And I mean, it changes. In any case, let's just do this for the moment. And this is, let this be this, where the M sub i's are minimal generators. Okay, there's always a unique set. We just take the smallest by divisibility, a set of monomials. And that's a unique set. So everything's nice here. And now we're going to we're going to define LCM of M1. We're going to take the LCM of all these monomial generators. That's going to be some monomial. And I'm going to call that monomial x1 to the lambda 1 times all the way up to xn to the lambda n. Some monomial, and that's what it is. Okay. So what is lambda I? So lambda I is equal to the largest exponent appearing in any of the M sub i's, M sub j's.
Do you intend a?
No, this is supposed to be an n. Absolutely not the same number of variables. Okay. Thank you. And so this is just a very simple thing. Let's as a running example, let's do the very simple one. Let's take I is equal to x squared xz and y squared z. Then the LCM of this is equal to what is it? X squared, y squared, and z. Okay. Okay, now we're going to make a definition of an Alexander dual in this case. I mean, really, the reason we're doing this is that square-free monomials got a really cool theorem out here, which is this thing here, this thing. And so we don't want to let it have all the fun. We want to instead get this to work for arbitrary monomial ideals. So here is the definition. I believe I'm not sure who actually came up with this definition first, but I do know that Ezra Miller sort of ran with it. Okay, so and it's in a good book for all of this stuff, by the way. Actually, I should write down a bunch of references. Miller-Sternfels has probably way more about monomial ideals than you ever want, but it has a lot of the it has everything you want also. So it's a nice book. So anyway, so here we have the definition now. We have an ideal I have this LCM here. Okay, this is a monomial ideal. And it might be, oops, like that. And I hat this, I mean, this is the Alexander dual, is going to be the following ideal. It's going to be generated by the products of the xi to the lambda I plus 1 minus beta I. And this is going to be over all things where beta I is greater than or equal to 1, where x to the I to the beta I for beta I greater than or equal to 1 is, this is a kind of weird way to say it, sorry, is an irreducible component. Irreducible, not primary component, irreducible. That, remember, that was just where that every irreducible component of a monomial ideal we knew was a product of a bunch of xi to some powers, but not all of them. Okay, so this is going to be whichever powers occur in that. Yeah, I think we need to, thanks. Of I. Now you might say, this is not so awesome because I have to know what the primary, the irreducible components are in order to write this down. That's true, but nonetheless, this is it. This is the Alexander dual of a binomial ideal. Okay, so does it make sense? Let's do it in this example. So I can actually write down the decomposition of this guy up here. So I is equal to x squared xz y squared z. And now what is an I-dual? Well, forget what I-dual is. This is equal first to x comma y squared intersect x squared comma z. I think that gives me everything in there. Here I get an x squared, I get xz, I get y squared x squared, which is in there, and y squared z. So that intersection, we don't need to intersect by any further. It's already in there. So these are the redundant irreducible components. And what else do we know about it? Well, let's calculate this. What this is? We have the LCM up there. So we take 2 plus 1 is 3 minus the 1. So this is going to be the first generator is going to be x squared, and then here we're subtracting off that thing that gives y, and then we also have xz. I think that's right, because here we get x squared, so that's again 2 plus 1 minus 2 is giving us the 1. Y doesn't appear in here, so we leave it out, and z is going to be the high power is 1. 1 plus 1 minus 1 is to the first power. Okay, so this is the Alexander dual of this monomial ideal. And you might say, well, wait a second. How are these related? Well, they're related. That's how we figured out what we wrote down what that is. Okay, so this monomial encodes it, but it's sort of upside down. So we have to take the complement of it, sort of. That's what we were doing before anyway. We were taking something and we're taking the complement of it, a coface, basically. But here we have exponents, so it's just a little more delicate. And now here is the really cool fact on these, which I am not going to prove here, just like I didn't actually prove this one either. So in fact, why don't we leave this out? No, I'll just rewrite the whole thing. Okay, so let's let x to the lambda equal the LCM of the minimal generators of the monomial ideal I contained in K of x1 to xn. Okay. So really what we want is that we want to actually have a way of computing that ideal that doesn't require us to immediately know what the answer is somehow. Then the minimal generators of I dual are those generators of the ideal x1 to the lambda 1 plus 1 up to xn to the lambda n plus 1. Okay, notice that that's these lambda I plus 1 things here. Okay, but this is all of them. That's an ideal. That doesn't look like it has a whole lot to do with I. But now we take the colon of we take I, this This is an ideal quotient of the monomial ideal with this thing, which is going to be another monomial ideal, which we can easily compute. But it's not all the generators of that, or all the generators of that are not divisible. In fact, that are not equal to one of these things, that are not, I'll say divisible by, but I think it's just equal to, divisible by xi to the lambda I plus 1 for I from 1 to n.
Plus 1 on the index of lambda or on the exponent?
It's on the exponent. Okay, so we're taking the LCM and we're bumping it up by one thing. By the way, this is actually the way to compute it also in the simplicial complex case. In that case, all the lambdas will be 1. And so we're taking x1 squared up to xn squared. And then we're doing this colon, and we're modding out by, we're not modding out, we're just removing the ones that were not changed. These are, every single one of these is in this ideal. So if I have a minimal set of generators of this thing, it's going to be just all the other ones. Yep.
So is this for all I or for one I?
Are not for any. So in other words, if it's basically the minimal generators of this thing might include some xi to the lambda I plus 1s by itself. And that'll be, you'll never have multiples of them if it's minimal generators. But as soon as you have a variable that hasn't yeah, the monomials you want in here are the ones that are of size smaller, that don't have this exponent on xi. So they'll have smaller exponents. So this is the key thing. This gives you this is an algorithm for compute. It's actually our second algorithm. The first one was to do the irreducible decomposition and do it. This essentially is giving you the same information, but it gives it to you directly without any choices in how you do the computation or anything like that. So, so in reality, this is giving you some sort of canonical canonical primary decomposition for a monomial ideal, even though it's not unique. So you'd actually see what happens if you take try x squared comma xy, for instance, and just see what you get from that. Okay. So anyway, so as an exercise, I would try proving the previous one and this one. I would probably do the other one first, even though this one does include that. But it's just more notation, and it's easier to see a way to it once you do it. But this is actually really pretty straightforward to compute. And there have been cases where I've done this in these biological applications where you have this huge amount of data and you get a monomial ideal out of it. I can maybe explain that sometime. And you're trying to, it's coming from data, and you're trying to figure out if it's consistent or what are the possible wiring diagrams of some system. And the wiring diagrams turn out to have to do with the minimal primes of the original ideal, but it's got thousands, maybe 100,000 generators and things like that. And there is there are computer science papers that basically say, wait a second, we can't even do this. This is an NP hard problem to compute one generator of this thing. Okay, and let alone all of them. And even for a square-free monomial ideal. Okay, so that's a hard problem, and so they sort of gave up. But I didn't know about that result, and so we were just doing this, and it was just working on pretty large data. So it really depends on the kinds of examples that you're doing. That's always a problem with complexity theory, is that it's a worst case scenario thing, and you might never come across the worst case. Yeah, that said, you might also hit it all the time, so you're not sure, but you know, you have to just take it a little, don't let it just stop you from thinking about something. And but in this case, we could compute all this huge number of things, like in a fraction of a second or something like that. And in that case, you wanted it to come out with a handful of small minimal primes that only involved a small number of things. But if it came out with a huge number, like 10,000 things, that probably meant that your data was not good to start with. So it's kind of interesting. There's all this kind of interesting relationship with that. And actually, I think after today we could write down exactly what that is. Maybe I'll do that at some point. We'll give it as an exercise. Okay, it is 6 minutes before. I do want to sort of say a word or so about where we're going and what we're going to do. So so we didn't do zero-dimensional ideals yet. Okay, but our goal now is given I an ideal. This is k of x1 xn as usual. We want to find a primary decomposition of I. Actually, there's only one of the things that we might want to find about it. And other things we might want to find are the radical of I. Okay? Or we might want all the minimal primes of I. In fact, oftentimes this is really what you want. This helps you get that, but usually it's one of these two things that you really want. You might, though, want the set of associated primes of I, or you might want the full primary decomposition. It's rare that you actually really need this, so that's why I'm bringing this up. So, but we want ways of computing all of, okay, that is this one. So these three things. These four things. Okay, so at any rate, that's what we're looking for. And the way we're going to do it is we're going to look at first the very special case where the dimension of I, actually that means that the dimension of R mod I is 0, i.e. The zero set of I over the algebraic closure is equal to a finite number of points. So geometrically, it's just a bunch of points, but they might have fatness to them. In other words, there might be, well, anyway, we'll have to play around with that. So this is going to be case one. We're going to spend at least the first hour next class on that. And this, it turns out, I always used to think it was absolutely trivial, but there's a lot of interesting things that go on there. And it's especially interesting because what we do is, in the general case, is we're going to reduce to this case. And the way we're going to reduce is, so reduce to this case. This is where we're going to use the algebraic independent sets. And there's a geometric way of thinking about this as well. But basically, if I have an independent set, this is going to be U is equal to a set of some of the xi's. I can think of my ideal I, and suppose it's an independent set. This algebraically independent set, which is problem 2 on the thing. Okay, but this is for an arbitrary ideal, not a monomial ideal. Okay, so if it's an independent set of I, mod I, and then here, let me give myself a little more room here. Then what I'm going to do is I'm going to do this, and not just an independent set, a maximal size independent set. I'm going to invert those variables in this independent set. And then I have all the other variables, x minus u. Okay, so this contains I times k of x, but it's a little larger than that. But this is zero dimensional. But over this field here. So, question? Or my oh, sorry. So this is going to be zero dimensional, so we can use this stuff up here. So this isn't just stupid set condition of a bunch of points. This is going to be where essentially you have your your finite, your zero dimensional over something else, which is a little more interesting. And so that's zero dimensional. So from this, we'll be able to compute this. And then we have to contract back. Well, this is fine. This gives you part of the contract back means intersect with the primary decomposition of this with k of x. We'll do all this next time. And the trouble is that doesn't give you everything. But what it gives you is a h in the ring R, actually in the ring k of x, k of u's, such that the original ideal I is equal to an intersection of stuff coming from this here, intersect I plus h to the some power L. Okay, this is our splitting principle that we had last time, the key lemma. This is going to be essentially I colon h infinity. But this is it. This is going to be already now decomposed. This is going to have higher dimension essentially, or maybe not, but it'll be, then we can do the same thing. We can recursively do this for this ideal and so on. And that's going to be essentially the algorithm for primary decomposition. Does it make any sense? So and actually, if we're only interested in minimal primes or things, we can take the radical, and then we don't have to do this h to the L, but we do have to take I plus h and then do that. The trouble with this process is this side here could potentially involve a huge amount of extra associated primes than are present for I. So we have to somehow, and this is not well set up. I mean, we have various people have different ways of trying to figure out how to reduce that redundancy. Because if you're spending a huge amount of time over here on stuff that you don't even need, then why bother? So you have to think about ways of doing that. Okay, the other thing is this thing here, the first thing is that we're going to use K as a perfect field. You remember what a perfect field is? You probably know all that stuff better than I do because you probably had it more recently in your field theory class than I did, but nonetheless, if it's a perfect field, then it turns out this all works fine. But what if it's not perfect? And you might say, well, who cares about that case? Because, but that is actually going to be a problem because if I do K, suppose I take FP, finite field, right? And I take one variable here, U. Let's say T. This is not a perfect field. This is not there. And in fact, if I take the polynomial x to the p minus t, this, so if I take inside of here, I take this of x, I have this kind of polynomial over an extension field of this factors in fact is a product. This is an inseparable extension kind of thing. And all of the algorithms that you find, okay, I'm going to also give you one more reference on primary decomposition. A good one, I think it's actually not bad. It kind of goes on, but it's Becker and Weisbennig. I don't know if there's two N's in that or not. But anyway, this is a book on Grosvenor bases. And if you look in chapters, I think, if I remember correctly, it's 8 and 9 talk about all this stuff. And he does a really nice job of proving everything directly. Some of it's stuff that you might already know. So you have to sort of sift through and figure out what you want. But nonetheless, it goes through and it shows this for K is perfect. And it shows you exactly how we'll boil it down in a slightly better way, I think. But nonetheless, if you want a place to read about things, this is actually not bad. Okay. That's all for now. Okay, see you next week.